All right, we're gonna go ahead and get started. We might finish these notes, and we might not. If we don't, I mean, if we do finish them, you'll just have your assignment tomorrow to do while you're sitting in here and everybody else. We won't have a for real Zoom. I told people sitting in here, your test is probably going to be Friday, so we will finish 4-3 tomorrow. Wednesday, you will probably have a review. Thursday, we'll probably go over that review, and then Friday, you'll have your test. So be ready for that test on Friday. 4.3, using studies wisely, you want to be able to describe the scope of inference that's appropriate in a statistical study. That one's not too bad. And then evaluate whether a statistical study has been carried out in an ethical manner. So researchers who conduct statistical studies often want to draw conclusions or make inference that go beyond the data they produce. Here are two examples. The U.S. Census Bureau carries out a monthly current population survey of about 60,000 households. Their goal is to use data from these randomly selected households to estimate the percent of unemployed individuals in the population. Scientists performed an experiment that randomly assigned 21 volunteer subjects to one of two treatments, sleep deprivation for one night or unrestricted sleep. The experimenters hope to show that sleep deprivation causes a decrease in performance 2 days later. So what type of inference can be made from a particular study? The answer depends on the design of the study. In the Census Bureau's sample survey, the individuals who responded were chosen at random from the population. Random sampling avoids bias and produces trustworthy estimates of the truth about the population. The Census Bureau should be safe making an inference about the population based on the results of the sample. And again, you'll learn exactly how to do that in just a couple minutes. In the sleep deprivation experiment, subjects were randomly assigned to the sleep deprivation and unrestricted sleep treatments. Random assignment helps ensure that the two groups of subjects are as alike as possible before the treatments are imposed. If the unrestricted sleep group performs much better than the sleep deprivation group and the difference is too large to be explained by chance variation, in the random assignment, it must be due to the treatments. Okay, you'll see this statement, this chance variation statement, over and over again. Okay. In that case, the scientists could safely conclude that sleep deprivation caused the decrease in performance. That is, they can make an inference about cause and effect. However, because the experiment used volunteer subjects, this limits scientists' ability to generalize their finding to some larger population of individuals. All right. So what you're going to figure out is if it makes a cause and effect, and then if you can actually apply it to the larger population. And they'll tell, again, we'll learn exactly when you can and when you can't. So let's recap what we've learned about the scope of inference in a statistical study. This little section right here that I'm about to do is what you need to know. Random selection of individuals allows inference about the population. Random assignment of individuals to groups permits inference about cause and effect. The following chart summarizes the possibility, so we're going to go over it one more time. All right, so what you're looking for is randomly selected and then randomly assigned. So if they were randomly selected, a yes, and they were randomly assigned, then you can make inference about the population and inference about cause and effect. If they were randomly selected, but not randomly assigned, you can make inference about the population, but not about cause and effect. You guys see how to read this. All right, so if they were randomly selected or not randomly selected, but they were randomly assigned, then you can do inference about cause and effect. So this was those volunteers. They weren't randomly selected, they volunteered, so that was a no, but they were randomly assigned to groups. So that's how you can make the cause and effect inference. So that's exactly how you read this chart. And you'll have to read it. You'll have to be able to read that chart. And you need to memorize it. All right. Well-designed experiments randomly assign individuals to treatment groups. However, most experiments don't select experimental units at random from the larger population. That limits such experiments to inference about cause and effect. Observational studies don't randomly assign individuals to groups, which rules out inference about cause and effect. An observational study that uses random sampling can make an inference about the population. The following example illustrates all four cases from the table in a single setting. All right. So vitamin C and canker sores, determining the scope of inference. A small town dentist wants to know if a daily dose of 500 milligrams of vitamin C will result in fewer canker sores in the mouth than taking no vitamin C. The dentist is considering the following four study designs. Get all dental patients in town with appointments in the next 2 weeks to take part in a study. Give each patient a survey with 2 questions. Do you take at least 500 milligrams of vitamin C each day? Do you frequently have canker sores? Based on the patient's answers to question 1, divide them into 2 groups, those who take at least 500 milligrams of vitamin C daily and those who don't. Design 2, get all dental patients in town with appointments in the next 2 weeks to take part in the study. Randomly assign half of them to take 500 milligrams of vitamin C each day and the other half to abstain from taking vitamin C for 3 months. Design 3, select a random sample of dental patients in town and get them to take part in the study. Divide the patients into 2 groups as in design 1. Design 4, select a random sample of dental patients in town and get them to take part in a study. Randomly assign half of them to take 500 milligrams of vitamin C each day and the other half to abstain from taking vitamin C for 3 months. For whichever design the dentist chooses, suppose she compares the proportion of patients in each group who complain of canker sores. Also suppose that she finds a statistically significant difference with a smaller proportion of those taking vitamin C having canker sores. What can the dentist conclude for each design? So think about that chart. Design 1. What was design 1?
Get everyone and ask them if they took more than 500 milligrams a day or not.
Okay. So the question is, I'm going to write this up here. Did they randomly assign it? And I'm going to call that RA. Or did they randomly select?
They knew neither because they asked everyone.
Wait a minute. Not there yet. We're going to go through each one, okay? So did they randomly assign them? Yes or no? Did they randomly assign them? Kyle, you can answer now.
No.
Why?
They picked everyone, like they picked the whole population they were studying.
Okay. Did they randomly select?
No.
Okay, so wait a minute. Let's look back at this one more time. All right. Get all dental patients in town with appointments in the next 2 weeks to take part in the study. Give each patient a survey with 2 questions. Do you take at least 500 milligrams of vitamin C, or do you frequently have canker sores? Based on the patient's answers to question 1, divide them into 2 groups, those who take at least 500 milligrams of vitamin C daily and those who don't. So remember, I kind of started backwards. So probably should look at randomly selected first. Did they select randomly the population, not the population, but the sample that they were choosing? What'd they say? Yeah, all of them. So did they randomly select? No. Remember, random selections like you take a part of it, like you put them in the hat, draw them, whatever. So random selection was the first thing that you wouldn't have seen because they asked all of the dental patients in town. So if you need to put that, you can put that. Random assignment means that they would randomly assign them to either the treatment or not. Did they do that? How did they assign them? How did they assign them to the 2 groups? Based on questions or based on answers to the questions. So in our chart, we didn't have random selection and we didn't have random assignment. So random selection, no, means that we can't have inference about the population. Random selection, random assignment, no, means that we can't have inference about cause and effect. So we cannot infer about the population or cause and effect.
Will we like have to start putting these in context of the problem?
Not on these. It's just asking you why. So, okay, one more time. Randomly select would give you inference about the population. Y'all got that? Inference about the population. Random assignment gives you inference about cause and effect. All right, design 2. I'm going to go backwards. I'm going to start randomly select. Did they randomly select the people? Very first sentence. Did they randomly select these people? No. Why? Good. Did they randomly assign them? Read design 2. Did they randomly assign them? Yes. How do you know? It says randomly assigned, randomly assigned. So look back at your chart. Look back at your chart and put it up at the same time. Random selection is a no, but random assignment is a yes. So what can we do? Can we do inference about the population? No, but we can do cause and effect. So we can infer about cause and effect.
So random assignment goes directly with cause and effect, and random selection goes with the population.
Yes.
Okay.
All right. So what does this mean? What can you infer about the cause and effect in this study? Does what? How? What do you think it's going to do? What does the vitamin C do? Nope. Other way around. Reduces. Canker sores. Isn't that what it says in the beginning to see vitamin C? Yep. All right, design 3. Random selection, random assignment. Is there any random selection? Come on, guys.
Yes.
Why?
It literally says select a
It says
random.
select a random.
Select a
sample.
random sample. Perfect. I know that y'all think it's crazy that I asked that, but people are not seeing it. So it literally tells you when it is selected, okay? Does it say they're randomly assigned? No, they are not
No.
randomly assigned. Good. So what can we infer about? Cause and effect or population?
Population.
Population.
Stop Snapchatting. Ah, I'm just kidding. Y'all are good. All right. So what would that be? What's the difference in this? Okay, so infer about cause and effect means that vitamin C reduces canker sores. But what is the difference about having it within the population? But I can't say cause and effect. I can say it has an effect on the population, but it is not a cause and effect. So I cannot say what I did before. I cannot say that vitamin C reduces canker sores. But what can I say about the population? What's happening? What was the outcome of the study? Guys, what are we trying to figure out? Okay, so if vitamin C reduces sores, so if it's cause and effect, we can actively say that vitamin C reduces canker sores. But if it's on the population, what that means is we have the same outcome, but we can't justify it with the vitamin C. So what that's saying is those taking vitamin C had fewer sores, but we cannot say that it's because of the vitamin C. So something else could be causing it, okay? All right, design 4. Were they randomly selected? Yes, were they randomly assigned? What can we infer? Population and cause and effect. So that means what? This is the difference. Causes a reduction in canker sores. And we can state that about the entire population. The challenges of establishing causation. A well-designed experiment tells us that changes in the explanatory variable cause changes in the response variable. More precisely, it tells us that this happens for specific individuals. In the specific environment. Of this specific experiment. A serious threat is that the treatments the subjects or the environment of our experiment may not be realistic. Lack of realism can limit our ability to apply the conclusions of an experiment to the settings of the greatest interest. All right, so we'll kind of talk about that right now. So do those high center brake lights required on all vehicles sold in the US since 1986 really reduce rear end collisions? Randomized comparative experiments with fleets of rentals and business cars done before the lights were required showed that the third brake light reduced rear end collisions by as much as 50%. But requiring the third light in all cars led only to a 5% drop. So what happened? So randomized comparative experiments with fleets of rental and business cars done before the lights were required showed that the third brake light reduced rear end collisions by as much as 50%. But now that they're required, it only led to a 5% drop. Why?
Because the crashes don't happen because of them not being there.
Not necessarily. How many of y'all noticed that every single car has that third brake light? Y'all notice it? You do?
Yeah.
You do? You notice it when you're driving? Every single car?
Not all the cars, but the ones where it has a working upper brake light.
Did y'all know every single car had that third brake light?
I don't even know what you're talking about.
The one, like, if you're driving a van or SUV, they're in the top of that glass.
Do all cars have them?
Yes, they do. Did you know?
Yeah, I've never noticed.
Why have you never noticed?
Because they're so insignificant.
I don't really care about cars that much.
Well, it's not even that. It's not even that, Rachel. What were you gonna say, Kyle?
They're so insignificant.
Hey, do y'all know the color of the chairs in my room?
Blue.
How do you know?
Every chair.
Every chair has it, right? So do you really notice it when you come in and say, oh my God, that's a blue chair? But if I put a yellow chair out there, would you notice it?
Probably.
Probably. Y'all understand what I'm saying? So before they were required, people were like, oh, checking it out. Look, that's new. That's cool. The turn signals on the mirrors. You guys notice those? I notice those every time they come on. Or the ones that are like the back, like on Mustangs and stuff, where they're like whatever. They're not like a single light. It like whatever. Anyway, but you notice those. It draws your eye in. Well, now that they're required, people don't pay attention to them. Does that make sense? So before they were required, people were like, oh, there they are. And yes, it probably did reduce it. But now what happened is people pay less attention. Again, because they're required, so nobody really, it's not out of the ordinary. It's nothing new. In some cases, it isn't practical or even ethical to do an experiment. Consider these important questions, and we're not trying to cause a debate or anything here, so we're just looking at this. Does texting while driving increase the risk of having an accident? Does going to church regularly help people to live longer? Does smoking cause lung cancer? To answer these cause and effect questions, we just need to perform a randomized comparative experiment. Unfortunately, we can't randomly assign people to text while driving or to attend church or to smoke cigarettes. Should say just the. The best data we have about these and many other cause and effect questions come from observational studies. I don't think anybody would be like, hey, let me smoke a bunch of cigarettes so I can get lung cancer. I'll help you out. So that's basically what they're saying. Is it sometimes possible to build a strong case for causation in the absence of experiments? The evidence that smoking causes lung cancer is about as strong as non-experimental evidence can be. So living with observational studies. We're not going to go over that. We're going to go back. We're going to kind of skip that. Anyway, all it talks about is there's been so many people with lung cancer tied to smoking that it's proven just by observational studies. What are the criteria for establishing causation when we can't do an experiment? The first thing is the association is strong. The association is consistent. Larger values of the explanatory are associated with stronger responses. The alleged cause precedes the effect in time. And the alleged cause is probable. So again, just like in the lung cancer case, the association is strong between smoking and lung cancer. It is consistent that smokers are usually the ones that get lung cancer. The more you smoke, the more risk you are at getting cancer. So all of these, if you fall in with that one, you can understand, okay? Medical authorities do not hesitate to say that smoking causes lung cancer. The U.S. Surgeon General states that cigarette smoking is the largest avoidable cause of death and disability in the U.S. The evidence for causation is overwhelming, but it is not as strong as the evidence provided by a well-designed experiment. conducting an experiment in which some subjects were forced to smoke and others were not allowed to would be unethical. In cases like this, observational studies are our best source of realistic information. All right, so I am going to stop there. The last little 2 paragraphs or whatever we'll do tomorrow for Zoom. And then, like I said, you'll have something on Wednesday to probably a review that you will do. And then we'll go over a review on Thursday, and then you'll have your test on Friday. So I'm going to stop sharing and stop recording.